Hi everyone, I'm going to present a joint work with Mikołaj Bojańczyk about first-order tree-to-tree functions. Our starting motivation for this work comes from these nice characterizations of first-order word-to-word functions. The first one is based on machines, called streaming string transducers. These are automata with the registers, as the one you can see here. The second one is based on logic, first-order transactions. So here we see a word as a logical structure, and we use first-order formulas to describe the link between the input and the outputs. So this is an example of a transaction which describes the reverse function. The third characterization is based on basic functions, which generate by composition the whole set of first-order word transactions. So these basic functions are called first-order list functions. An example here is the reverse function, but of course we have many other such functions, and we saturate them by composition. Now let us move to the realm of trees. Well, actually there are multiple models of trees in the literature, but the one that we will focus on is that of ranked trees. To construct a tree, we need a ranked alphabet, which is a set of elements having arities. So this is an example of a ranked alphabet. It contains a binary element, a unary element, and a nullary element. And the tree is obtained by combining these symbols by respecting the arities. So this is an example of such a tree. And now that we know which trees we are talking about, we can wonder if we have the same picture as we've seen for words. And the situation is kind of promising because we have again characterizations based on machines, streaming tree transducers, and on logic, first-order transactions but interpreted on trees. And what was missing to this picture is a set of basic functions which generate, by composition, the whole set of first-order tree transactions. So this is precisely what we've done with Mikołaj. We baptized our basic functions prime tree-to-tree functions. But before presenting them, let me give you an example of a first-order transaction. So here, this example is based on lambda terms, which can be seen as trees over a ranked alphabet. So if we fix a set of variables x, then we can consider this ranked alphabet, which contains an element x of arity 0 for each variable, an element of arity 1 for each variable, lambda x, and a binary element, here, the application element. And a lambda term is a tree built over this ranked alphabet. Now, if we focus on affine lambda terms, which are those lambda terms where each bound variable occurs at most once, then we can see that normalization or beta reduction always terminates. And since beta reduction is confluent, we can define for each affine lambda term its normal form. So here you see the normal form of this lambda term, and we can see the normalization function as a tree-to-tree transaction. Actually, it's not very hard to see that normalization of affine, simply typed and finitely typed lambda terms is a first-order transaction. Here, by finitely typed, I mean that we need only a finite set of types to type the whole set of lambda terms under consideration. Okay, so now let's move to prime functions. I told you that I want to characterize tree-to-tree functions, but actually the prime functions I will use have more complex data types, more complex than trees, I mean. And this is not mandatory, actually. We could make a different choice, but we wanted to avoid precisely encoding data types in the prime functions. For instance, if we want to talk about a pair of trees, we can of course encode them as a single tree and encode the projection function as a tree-to-tree function, but we will avoid all these complications by having the pair data type and the corresponding projection function as a basic function, as a prime function. So types, of course, generalize the data type of trees, but they will also generalize ranked alphabets. And this is the reason why our types will be ranked sets, meaning that each inhabitant of a type will have a arity. So types are defined inductively, the base case being the set of all finite ranked sets, and the ranked set, here I denoted by 1, which contains a single element for each arity. So this is an element of arity 0, of arity 1, etc., etc. And we have some few type constructors. The most important one is the constructor T of terms. So the inhabitant of T sigma are almost trees over the ranked set sigma, at the exception that these trees can have dangling edges. Their number is the arity of the element. So this is an element of arity 2. And trees are just terms of arity 0. They don't have dangling edges. The second type constructor is the constructor of pairs. So here is an example of an inhabitant of this type. It's just putting side by side an element from sigma and an element of gamma, and the arity is the sum of the two arities. So this is an element of arity 3. The third type constructor is the coproduct. So an element of sigma plus gamma is either an element of sigma or an element of gamma. And here we add an index, either 1 or 2, to say from which copy comes the element. And again, the arity is inherited from those of sigma and those of gamma. Actually, we have another type constructor, but I'm not going to explain it here in this presentation. I don't really need to explicit it, but of course you can check it in the paper. Here is an example of a complex data type, the type of terms of terms. So this is an example of an inhabitant of T of sigma. This is a tree whose nodes are themselves terms. So sorry, this is a term whose nodes are themselves terms. Now let's move to prime functions themselves. So all prime functions will be arity preserving, meaning that they map every element of a certain arity into another element with the same arity. I classified them here into coherent categories. The first one is basic functions. It contains all arity preserving functions with finite domain, and functions of this type, which are arity preserving. And this function maps each element of sigma to the unique element of 1, having the same arity. The second category, I call it the non-controversial functions, because it contains all the function that we would like to have when we have the sum and the product data types. So it contains the projection, the coprojection, and all those functions expressing that plus and the tensor are commutative, are associative, and distributive, one over the other. Here I give you only the types, not the precise function, but actually they can be easily guessed from the types. The third category is the class of functions expressing that the set of terms forms a monad. So we have this unit function, which maps an element of sigma to a term containing a unique node, which is this element of sigma. Then the flattening function, or the product function, which flattens a term of terms into a term. We are not yet done with prime functions. We have another function called factorization, which regroups the elements of a term into blocks having the same type, as you can see here in the picture. Another important prime function is depth first search, which takes as input a term and outputs another one representing its depth first traversal. And of course, we have many other small functions which are about this data type I didn't present, but you can see them in the paper if you want. And of course, we saturate all these prime functions by composition here, but also by lifting them to the type constructors. For example, if we have a function from sigma to gamma, then you can get the function tf from t sigma to t gamma, obtained by applying to every node of an element of t sigma the function f. This is, in some other words, the map function. And we call derivable functions the set of functions obtained from prime functions by these combinators. The main result of the paper is that derivable functions coincide with first-order tree-to-tree transactions. Actually, we have also characterizations of MSO and chain logic tree-to-tree transactions based on basic functions, but they can be fairly easily obtained from the main result. So I will not present them here in this talk. Now, to prove the main theorem, there is of course two directions. The first one is proving that derivable functions are tree-to-tree transactions. And this is easy because we only need to check that each individual prime function is a tree-to-tree transaction. And this is not very hard. We designed them to be tree-to-tree transactions. Of course, the hardest part is to decompose each tree-to-tree transaction into a composition of prime functions. So this is a very technical result, and we go through automata to prove it. But let me give you just a hint on how we prove it. So to get this direction, we show that every first-order tree-to-tree transaction can be decomposed into three functions. The first one is what we call a first-order relabeling. The second one is normalization of lambda terms. And the third one is a function called infolding. Now, to show that a first-order transaction is derivable, it is enough to show that each of these three functions is derivable. So let me say a word about each of them. So first-order relabelings are a very particular case of tree-to-tree functions where the shape of the tree doesn't change, but the labels may change following some first-order unary queries. So in this example, we have this first-order query which selects the nodes that will become green. For instance, we can imagine that this formula selects the root of the tree. We have the second unary query which selects the nodes that will become red. And we can imagine that it selects the leaves of the tree. And finally, we have this formula which selects nodes that will become gray, and we can imagine that it selects the inner nodes of the tree, so nodes which are not the root nor the leaves. So the first order relabeling of this tree is this tree. Now, to show that first order relabelings are derivable, we can be tempted to proceed by induction, but this will introduce some new variables which we don't know how to handle. So to solve this problem, we go through an equivalent formalism, which is temporal logic for CTL that you can see here. So it's very close to CTL with this additional child formula. And we have this remarkable result by Schlingrove, who shows that first-order unary queries are equivalent to 4CTL. So the advantage of this formalism is that is variable free. And now we can prove that our first-order relabelings are derivable by induction on the structure of this formulae, which is very easy now. Which becomes very easy. The second ingredient to prove the main result is to show that normalization of affine simply type lambda terms is derivable when restricted to affine simply and finitely lambda terms. Well, as I said at the beginning, this normalization function can be seen easily as a first-order transduction, but it is much more difficult to derive it using prime functions. But the idea here is to notice that normalization follows very roughly a depth-first traversal in the input lambda term. So here, the depth-first search function plays a key role to prove that normalization is derivable. The last ingredient is the unfolding function, illustrated by this picture. It takes as input a term of this shape and outputs the term where the links between the links between the boxes are turned into direct links between the inner nodes in the natural way. So showing that this function is derivable is certainly the hardest part of the proof. It relies in particular in Simon's factorization force theorem. So these three ingredients, when we get that unfolding is derivable, normalization is derivable, and first order relabeling is derivable, are enough to show that whole first order 3-to-3 functions are derivable. So let me conclude. So by giving some directions of future work. We can generalize the work I presented here following two axes. The first one is by extending the structures under consideration, for example, by considering graphs instead of trees. The second direction could be to consider more expressive classes of 3-to-3 functions, for instance, the polyregular 3-to-3 functions. And finally, we can think about some implementations of this work. So I think I should stop here. Thank you very much for your attention, and of course, don't hesitate to ask me some questions. Thank you.